Good morning everybody. So, we are discussing about the TGA thing, the thermogravimetric analysis, and where we have seen that we can have different samples starting from any organic material to any pharmaceutical sample. So, what we are interested to know at this point is that if we have a typical metal salt or metal ion salt, such we all know that Mx or Mx2 or Mx3 or M2X3 all like this, and if we want to know the corresponding composition of these metal ion salts, because what we want to know is that for all these things, depending upon these compositions, we can analyze in any unknown sample, such as of your water sample or the groundwater sample, the presence of the metal ion which is M with a charge of N plus, or the corresponding anions, it can be X, it can be X2 minus, or it can be X3 minus. So, combination of these two of different stoichiometry can give rise to the different formula of these compounds. So, why these are so important? Because last time we have discussed that we can have calcium 2 plus or magnesium 2 plus in the solution, and that causes the hardness of the water, and we want to determine the corresponding hardness of these things. Similarly, all these things, they are not very simple anionic species like chloride, bromide, iodide or fluoride, but they can be very complex one like arsenate one. Similarly, these metal ions, it can also be the corresponding oxo anions such as MoO4 2 minus, the molybdenate ion. So, these oxo cations and the oxo anions, because this will also be converted to the typical anionic form. So, these anion, the presence of these and the corresponding combination of these in the samples are also important, not only for these when we add X minus, X2 minus or X3 minus to the corresponding unknown cationic form or the metal ion, we get a precipitate, and we take the corresponding weight of the precipitate, that is the corresponding gravimetric estimation or the gravimetric analysis. And in this particular formula, suppose if it is Mx2 and certain number of water of crystallizations. So, these water of crystallizations are very important, and starting from all these things what we have seen in our last class, that determination of calcium as calcium oxalate or magnesium as magnesium oxalate in any such thermogravimetric analysis will tell us the corresponding level of hydration, that how many water molecules are present as water of crystallizations. So, the determination of these things are also important in any pharmaceutical sample or the cement sample and so on. And also one more example for this type of thing, that means the M part and the X part, is for analyzing the minerals, the ores and some important compounds. If we want to measure something based on the chromium, so chromium based ore, we all know that chromium is present in steel and many other sophisticated alloys. So, chromium in which form? We call it as chromite. So, chromite ore we all know. So, chromium in which form and what is the corresponding composition of these things, that we should know. So, analyzing this thing, that means if this particular chromium is present in this form, or we know that if we heat somewhere, because all these thermochemical reactions are very important to understand these as, because this is the corresponding molybdenum sample in +6 oxidation state, and the corresponding oxide of molybdenum we all know, that is molybdenum trioxide. But we are talking as the corresponding anionic form, where the metal ion is present in the corresponding hexavalent state, and the corresponding composition of these anions will also tell us that how we can purify the corresponding any ore. It can be hematite, it can be magnetite, and all these things. So, the treatment of these, and this is the thermal treatment. So, the thermal treatment of these things can give rise to either that chromium trioxide species, or sometime Cr2O4 species, or sometime we find that some other metal ion like iron is also present with this particular chromium oxygen combination. So, several other metal ions are also present. So, percentage composition is always important to know, and which is directly related to the purity of the sample. So, now we take the example, because we all know that this can be your corresponding simple oxide or some heterometallic oxide of chromite. So, this can be chromite, the formulation for chromite, and this iron bearing chromite is also there, and we can have different charges of all these things. And along with this treatment, that means the thermal treatment, we always know that if we do it in presence of air or oxygen, because this O2 is present with your air. So, with this oxygen and all these things, so during this heating process, that O2 can go out, or sometimes this the species or the corresponding compound which is left over, if it is highly reactive with your O2 at a high temperature, it can again give rise to the corresponding oxides. Okay. So, now we will take two such examples where the chromium samples can be useful, or the chromium is present along with oxygen. So, one such your Ag2Cr O4, and another is Hg2Cr O4, and all we know that these particular species containing CrO4 2 minus is the corresponding chromate anion or chromate ion. So, if we have these two, and what change we can have here, here only the heavy metal ion mercury is present in +1 oxidation state, and here silver is present as silver 1. So, these two will not be the same one in terms of its that chromate content, but depending upon its corresponding presence of the different cationic form or the cations, it can have different stability. So, when we heat it from room temperature, we get the TG plot like this, where we have the corresponding stabilization also after some time. So, what we get? We get these as the corresponding degradation plot of silver chromate, and the corresponding one for mercurous chromate is like this, and then we have this, and it goes like this. So, what we initially find, or what we initially try to locate or try to detect, is that it can have two wet losses. So, this is your corresponding change in mass, which is your delta M value. So, this initial mass loss, what is happening till 92 degrees centigrade, what we can guess that this particular drop, and the amount of mass loss is also not very high. So, this particular mass loss is due to the corresponding one, that means loss of wash water. That means whatever water has been used for washing the precipitate, because this silver chromate, what we know that we can have the typical salt of this, which is water soluble, is sodium chromate, and if we can go for the corresponding cationic metathesis of this with any silver salt like silver nitrate, we get this as the corresponding silver chromate salt. So, when we got that thing, that means addition of this sodium chromate which is soluble in water, so is a solution in water, and addition to that on the corresponding say silver nitrate solution give rise to these things. So, whatever we do here is the corresponding one where we get the precipitate from the saturated solution, and we have to wash that precipitate to remove the corresponding cations like sodium which we do not want, and corresponding anion as nitrate. So, basically this washing, the precipitate washing is required for the removal of sodium nitrate. So, sodium nitrate we basically remove from the medium, and such that we can have comparatively very pure sample of silver chromate. So, initially what we see that there is a loss. So, the loss of wash water if you do not have any water of crystallization in this, because this sample the water of crystallization is not there. So, this particular mass loss will vary depending upon its washing liquid present. So, if we dry it for this particular one, so not only the water of crystallization which also sometimes goes at this particular temperature range, but also the water which is trapped inside the precipitate can also be removed by this temperature which is below 100 degrees say. So, we keep on increasing the temperature for this particular one until we reach a temperature of 812 degrees centigrade, because at this particular point there again we find a typical delta M value, that means the typical mass loss corresponding to some reaction, corresponding to some chemical reaction or the modification from one phase to the other, and it is complete at 945 degree centigrade. So, at this particular temperature range, this particular silver chromate is not stable. So, what we get over here, the corresponding reaction for the thermal decomposition of silver chromate like that of our calcium oxalate or magnesium oxalate, what we have seen in our previous class. So, this silver chromate Ag2CrO4 will start decomposing from 812 degree centigrade, and the typical pathway basically what we get is the formation of the metallic silver. You see very interesting reaction from here, that we are not getting silver oxide or any other silver form which we can have some other anionic species, but the metallic silver will be eliminated from there, and 2 of the oxygen. So, we have 2 of these silver chromate to be considered for your mass balance or the formula, and we have Cr2O4 as the solid. So, which is your chromite sample. So, the typical weight loss in this particular process due to this particular change in the mass in the y axis is due to the corresponding loss of dioxygen. So, what we see is a very interesting observation at this point, that some time back we have seen that some species or some material or some compound can be reacted at high temperature, because it is a pretty high temperature of 812 degree centigrade that can react with the oxygen present in air or in some oxygen environment. Probably you do not have any other environment maintained as an inert atmosphere like nitrogen. So, this oxygen is going out. So, weight loss at this particular point is due to the amount of oxygen which is being eliminated from the sample, but this is also solid and this is also solid. These two will remain in the crucible of the thermogravimetric apparatus or instrument. So, these two, so the combined weight of the metallic silver as well as the chromite sample will be there as the residual weight on the crucible sample. Only weight loss can be due to the corresponding dioxygen which is being removed from the sample. So, now if we take, we see that when we add silver nitrate, then here also we can add mercuric nitrate. So, is very easy to remember and easy to learn also nicely, that we will be using simply the nitrate salt of another metal ion such that we get the precipitate of mercury chromate. So, is the mercurous chromate, mercury 1 chromate, and its corresponding thermal stability also tells us that in this particular time the loss of was water can be removed at a low temperature up to 52 degrees centigrade. Then at a low temperature again at 256 degrees centigrade, we can go for the corresponding mass loss due to the decomposition of mercurous chromate, which is completed at a temperature of 671 degrees centigrade, and we go like 945 and we crossing over here as till 940 degree centigrade. Because all these cases, the thermogravimetric analysis, what we do is basically most of the time we just go for a temperature beyond 1000. So, we will talk at some time that what are the crucibles we should use which can sustain the its stability, that means crucibles should not be melted away, and that particular stability for a particular crucible is also important because the crucible material should not react with the sample which are being heated in that particular crucible. So, what we find that if we have this again this loss of water, so like the previous case, so loss of water over here and our anhydrous, that means no water content is there, neither in the form of the trapped water or in the form of water crystallization is there. So, this anhydrous form is stable at this temperature range. Then we go and crossing a level of 256 to 671 degree centigrade. So, what we see that this particular one, like that of our decomposition of silver chromate, this will also take place over here. But if we consider that this mass loss and this mass loss are not same, we should have something in difference we should think of. So, in this particular case, the reaction, the thermal degradation process is completely different. So, what happens in this particular case is you have the same type of silver chromate, because the formula will be very much similar to that of your silver chromate, but the formation of these, what we are seeing last time, that metallic silver, the separation of is that of your metallic silver, but here no such metallic mercury will be formed because the stability of mercurous oxide is there. So, it is forming as oxide only and no such chromite is forming, that means Cr2O4 is not forming, instead we have simple mononuclear chromium trioxide will be forming. Okay. So, this is in other aspect, that means precipitation part. Here also we are talking about the same way your precipitation reaction. So, what we see that these two things are completely different, but no O2 is coming out from this particular reaction also, which is also very interesting to know. So, what we see, why there is a mass loss or weight loss? Why there is a mass loss? Because the product of this reaction, product of this thermal degradation reaction is a very simple one, that in one case we get oxide, in another case is also oxide. This is low valent oxide because mercury is still present in the mercurous mercury, but chromium is typically hexavalent, which was originally also in the hexavalent state. So, no oxidation and no reduction is taking place, but here we have seen that in this particular case there is a reduction of the silver ion was present as the silver 1 and the reduction process is taking place. That is why we have the corresponding chromite formation. So, in this particular case also we have this oxide formation, but we should know at this particular temperature, which is pretty high at this point of 671 degrees centigrade. So, whether this mercurous oxide is stable at this particular temperature as a solid, which will be your residue on the crucible, but it is not so. It will be lost from the crucible by sublimation. So, which is a typical chemical process. We all know that sublimation is nothing but the corresponding solid state of that what is forming immediately on the crucible. The solid formation of this mercury oxide, mercurous oxide, will immediately go to its vapor state. That is called its corresponding sublimation. So, the corresponding wet loss at this particular point is due to the corresponding loss of your Hg2O. So, this loss of Hg2O, we should be very much careful at this point to know that this mass loss will correspond to only the corresponding loss of your mercury as mercurous ion and its corresponding oxide. So, whatever mercury will be present in this particular sample will be lost as the corresponding mercurous oxide. So, any sample like this, if we do for its corresponding TGA, we will find that the mercury salt, if we do in air, because this is also in air, the heating in air, this is also in air. So, heating in air sample will give rise to this as well as the chromium trioxide sample. So, this chromium trioxide sample will remain on the crucible, and whatever the leftover wet of the sample will be there is due to the presence of that particular chromium trioxide. Okay. So, this is the thing that we get the corresponding wet loss for all these things. Then if we take another typical sample, which is FeS2, is not your FeS, what we know as your ferrous sulphide, but this particular one is present as S2 2 minus. So, is a polysulfide. We call this sort of species as polysulfides. Polysulfide, because we all know that sometimes there will be charge, and if we have x number of these sulphide ions are present having n minus charge, we get this form as the corresponding polysulfide, and these are very good source of elemental sulfur, which is sulfur 0 as well as the sulphide ion. Because if you think that this can be broken into S0 and S2 minus, so this simple polysulfide species, the anionic species, can be a very good source of both. It can be a source of elemental sulfur as well as it can be a good source of sulphide ion. So, now if we think that slowly we are getting experienced to know or tell or comment on the sample what can be analyzed by TGA. So, one such sample is this thing, and if we elaborate the process, that means we want to more about their corresponding nature, that means the characterization process for this due to this particular thermal analysis, that we will do, and we will maintain some atmosphere, because the atmosphere all the time for any TG thermogravimetric analysis play an important role. What is your atmosphere? So, the atmospheric gases, because if we go for the corresponding analysis and the gas is evolving out, so that is one particular process, but there is another process where gas can be reacted with that particular sample, and we can also maintain something which is inert and we heat it. So, we basically want to see the temperature effect on FeS2 in presence of air, that means in presence of O2, and in presence of N2, that means the nitrogen, such that at high temperature this oxygen can react with this. So, what will form? So, what we can see that it can give rise to so many things, so many alternative things you can think of, and you can understand all these in a form that if we find that the typically this particular one at this particular point, because oxygen can oxidize both these two, that means if iron is present in the lower oxidation state, say of ferrous ions, it can be oxidized by this oxygen to ferric ion and then oxide formation. So, if we have the corresponding oxide formation, and in other case also we can oxidize the sulfur component or the sulfur part of the compound to its corresponding sulfides, and these are the two options, but the third option is the immediate conversion of the compound or FeS2 to another compound which is based on the sulfate. So, what we see here is a very simple one, where this, if we consider that you have S2 minus is not S1 minus, otherwise it will be the iron 1, because all these things can happen in the solid state where non-stoichiometric species can form very easily, which is not possible in case of your solution. So, this is your ferrous species then, and what is forming over is your ferric. So, you oxidize your ferrous iron to the ferric, as well as your sulfur will immediately oxidize to sulfate ion. So, this is basically the formation of corresponding ferric sulfate in this particular process, and oxygen is introduced into your solution, sorry, in the solid state, that means formation of the sulfate. So, we will have weight gain. So, we will gain some weight at this particular point, and we must have some temperature range for its stability. So, within a certain temperature range, you have the corresponding stable ferric sulfate or the formed ferric sulfate in this particular way. And we should also know at this point that what will happen if we go, that means further rise in temperature, what will happen? So, at this point the further rise in temperature will give rise to something where this may not be stable, this can undergo decomposition, and what we are looking at the very first step or the very first position at the lower temperature range was not happening. That means, the oxidation of iron to its oxide and oxidation of sulfur to its the sulfur oxide. This is happening in the second step at a high temperature, where you find that your Fe now present as ferric ion will be converted to your ferric oxide plus your sulfur will be converted to whatever sulfur you have as sulfate ion will be converted to sulfur trioxide. So, this is a very delicate process at this point, because the delicate step in this case is because the sulfur trioxide formation at a very high temperature, and atmosphere is also in air and oxygen. So, we expect that the sulfur trioxide is the most stable oxide form of the sulfur will be there, but it so happens that instead of these three will break, these three of the sulfur trioxide will break again into sulfur dioxide and oxygen back, what we have been utilizing from air or from the dioxygen environment. So, this sulfur trioxide formation, it will leave the crucible and it will go out from the corresponding chamber, the sample chamber, and it will go out from the instrument. So, only thing this as the solid, this solid of ferric oxide will remain on the crucible and will take or will carry the weight for ferric oxide only. But what happens if we heat the sample, same sample? So, because it is a good example for that, we can have two different types of reactivity of FeS2. So, in this particular case, in the nitrogen environment, oxygen is not there. So, oxygen will not so many things of this sulfate formation, this oxide formation, sulfur trioxide formation and sulfur dioxide formation and O2 back. is not happening over there. Instead, this will break into the most standard one what we were talking about. The very first discussion we started, that we know that the ferrous sulphide is a analytical compound what we analyze for your iron content in any unknown sample or the detection of H2 minus in any unknown sample is the formation of ferrous sulphide. So, it will be decomposed into FeS plus S. So, in this particular case also, if that particular temperature is very high and if this particular elemental sulfur is volatilized SiO, we can see only in that particular case some weight loss due to the decomposition or breakdown of your FeS2 to FeS and S. So, now we just see that how this TG thing can also be useful for its application, as well as the corresponding DTG use of your DTG thing. How the DTG can also be useful, because sometime if your TG is only not helpful, we can go for its corresponding derivative one. So, what we see and what we have seen so far is the corresponding TGA and DTG plot now, because the first plot is well known to us, because this is the corresponding heating of the corresponding calcium oxalate, and we have seen that in case of the heating of calcium oxalate in any furnace and using the corresponding crucible. So, we will have 1 loss, 2 loss and the 3 losses. So, first loss is due to the loss of water of crystallization, and which is not very high. So, starting from say 87 to say around 83 or 4. So, certain percentage of 2-3% of weight loss. So, 2-3% of this weight loss basically gives us something where we find that typical water of crystallization is going out, is not the wash water, because we have also discussed the loss of water is due to the corresponding wash water, but in this particular case the crystallization of water which is going almost above 200 or very close to 200 degrees centigrade, and in the second step we get the corresponding formation of calcium carbonate with the evolution of carbon monoxide, and in the third step we all know that in that particular case it is the corresponding degradation of calcium carbonate into oxide and carbon dioxide. So, if these 3 decomposition steps or the removal step of water, CO and CO2, and these corresponding steps is very difficult to identify all these things, because if the inflection point is not very sharp and if you have a very broad one. So, how to pinpoint the exact temperature, what we can prescribe that is the exact temperature for your weight loss. So, what we see that if we go for the corresponding stepwise decomposition of calcium oxalate with a mass of this and a heating rate of this under nitrogen, we see the corresponding derivative plot, because it is the weight loss, it is not weight gain. If it is weight gain the plot will be on the other side. So, at this particular point you see it will be very close to 200 degrees centigrade. So, exactly we can pinpoint the temperature for your loss of water of crystallization. Similarly, the second loss due to the loss of carbon monoxide is known now as the above 500 degrees centigrade, and for the third loss is due to the removal of carbon dioxide and formation of calcium oxide is very close to 800 degrees centigrade, because this one is almost continuous and we do not have very sharp and very immediate inflection point for this particular plot. But when we go for the derivative, the rate of change of that mass with temperature, mass loss with temperature, we find that a minimum will be available. So, detection of that particular minimum when we go for the derivative, the first derivative plot. So, that first derivative plot will basically give us that particular thing when we can pinpoint the temperature, where we can say that calcium carbonate will be decomposed at this particular temperature. So, this is not only true for calcium carbonate, but any other carbonate salts we can get the corresponding DTG analysis, and which is very important coming from your TGA to your DTG plot. So, from your TGA to DTG plot we get something difference, and we instruments we can have now, and all these new instruments are nowadays, they automatically record at the same time the TG plot as well as your DTG plot, and sometimes we can analyze the mixtures of these, that means mixtures of magnesium carbonates and the mixtures of magnesium carbonate as well as calcium carbonate for the typical analysis using your DTG technique. Thank you very much.